In this example, we'll sketch the graph of the rational function x squared plus 3x plus 2 divided by x minus 1. Like before, we need to find the y-intercept, the x-intercept, the vertical asymptotes, and the end behavior. To find the y-intercept, we want to look when x equals 0. Evaluating our function at 0, we get 0 squared plus 3 times 0 plus 2 over 0 minus 1, which reduces to negative 2. So the y-intercept is the point 0, negative 2. For the x-intercept, we look when y, or our function, is 0, which leaves us with the equation to solve 0 equals x squared plus 3x plus 2 divided by x minus 1. But we can solve a rational function equal to 0 by solving when the top is 0. So we need to solve the equation 0 equals x squared plus 3x plus 2, which we can do using the quadratic formula. If you'd like to see the steps of this done out, you can click the link to the left now. Solving x squared plus 3x plus 2 equals 0 using the quadratic formula, we find that x is either negative 1 or negative 2. So our x-intercepts are the points negative 1, 0 and negative 2, 0. For the vertical asymptotes, we want to know when our denominator is 0. We want to know when x minus 1 is 0. But this is easy to solve by adding 1 to both sides to get that x equals 1. Which means we have a vertical asymptote at the line x equals 1. Now for the end behavior, we want to know what happens to our function as x goes off to positive or negative infinity. But we saw that since the degree of the numerator is bigger than the degree of the denominator, we need to use our polynomial division. If you'd like to see the steps of this done out, you can click the link to the right now. Doing polynomial division, we get that we can rewrite our function f of x as x plus 4 plus the remainder 6 divided by x minus 1. And as x gets very large, 6 divided by x minus 1 gets very small. It goes to 0. So at our ends, our function f of x behaves like the line y equals x plus 4. This is called a skew asymptote. Now, like we did for polynomials, we need to check if our function is positive or negative on some of our intervals. And since there are no more x-intercepts, we know that f of x cannot change from negative to positive or positive to negative, except at our two x-intercepts or the vertical asymptote. Now let's look at each interval one by one. For x values before negative 2, we know our function needs to behave like the line y equals x plus 4 as x gets bigger and bigger. So to the left of negative 2, our function approaches that line. Similarly, on the right-hand side, our function needs to approach the line y equals x plus 4 as well. And near x equals 1, our function is either going off to negative infinity or positive infinity. But since the line y equals x plus 4 is positive, f of x cannot be going off to negative infinity near x equals 1. Otherwise, we would have another x-intercept. So we know our function approaches positive infinity near x equals 1 and approaches the line x plus 4 as it moves off to the right. Now between the x-intercept negative 1 and 0 and our vertical asymptote at x equals 1, our function passes to the point 0, negative 2. And since our y value is negative at this point, our y value must be negative for all points in between. And all that's left to check is between negative 2 and negative 1, which we can do by looking at the x value, negative 1.5, which when we evaluate f of x at negative 1.5, we get roughly 0.1, which is very small, but is positive, which means that f of x is positive between negative 2 and negative 1. And finally, we have the graph of our rational function, x squared plus 3x plus 2 divided by x minus 1.